We have already discussed question 1, 2, 3 of question paper 4143 of the 970 in chemistry of the examination series May-June 2024, and in this video we'll be discussing question 3 to question 6. So let's go ahead with question 3. We have to discuss question 4 to 6, and so here is question 4. It says define standard electrode potential E0 including description of standard conditions. Now, what is an electrode potential of an half cell? Electrode potential is the voltage. It's the voltage of a half cell compared to the standard hydrogen electrode, compared to the standard hydrogen electrode when the electrolyte have the concentration of 1 mole per dm cube, with, if gas is present, then 1 atm, that is 101 kilopascal also you can write, and 298 Kelvin, that is the standard temperature. So these are the standard conditions required because it's written describe the standard conditions and define standard electrode potential. So here is the definition including all the standard conditions. I am not writing the full sentence because that's not required. What is important is the 3 standard conditions of the half cell. Okay, the next part says an electrochemical cell is set up to measure the electrode potential of the silver ion to silver electrode. Draw a label diagram of this electrochemical cell. Include all necessary conditions. It is not necessary to state conditions used, only the necessary substances. Okay, so let's draw on silver ion to silver electrode, and that has to be in comparison with the standard hydrogen electrode. Now my diagram may not be very specific because I'm drawing on a screen, but yes, I'll try my level best to explain all the necessary conditions required here. This is the standard hydrogen electrode I'm trying to draw. Okay, it should have an platinum electrode, so here is a platinum electrode. Let me draw a little bit again. There is some mistake. Okay, fine. Let me extend it because it was too small. Yes, we can draw a bell jar. Yes, that's how it should look. Okay, that's a bell jar, and here should be a platinum electrode. So this is a platinum electrode. Fine. So that's an hydrogen electrode that has to be connected with a salt bridge to another half cell, which is a silver electrode, silver half cell. Okay, so this is another silver half cell. Now I should draw a silver electrode, now maybe an electrode, and with silver ions as an electrolyte. So silver electrode is drawn, so I should label this as silver electrode, where I'll draw it as solid. Let me fully label it, and then I should also mention this is Ag ions, that is the electrolyte in aqueous form, that has to be 1 mole per dm cube. Okay, yes, and both the electrodes are connected by a voltmeter, so that also has to be written voltmeter. I should label this as salt bridge. Again, this is a platinum electrode because that is standard hydrogen electrode. The electrolyte again has to be the electrolyte carrying hydrogen ions at 1 mole per dm cube. So hydrogen ions in aqueous form at 1 mole per dm cube. Concentration here should be the hydrogen gas. Again, that should be at 1 atmospheric pressure, and 298 Kelvin has to be maintained. So I'm writing it here. This is how actually you need not mention state conditions used, so we need not mention the conditions. So we can remove away with the 298 Kelvin and 1 mole per dm cube also. But then hydrogen electrode, platinum electrode, silver electrode and silver ions as electrolyte has to be mentioned. Here it's clearly written no state conditions used, so you can omit the concentration 298 Kelvin and 1 atm. Fine, this is how you should be drawing the half cells, and that carries 3 marks for all the parts. The next part is a separate electrochemical cell is set up using a lower concentration of silver ions than used in B1. B1 is standard with 1 mole per dm cube, but then a silver ions with a lower concentration is used. Suggest how the electrode potential E of the silver electrode would change from its standard value. Explain your answer. Now if I write Ag, okay, I'm writing it here. If I write the equation, it has to be silver this way. Now what is asked is that the silver ions are at lower concentration, so the left hand side is having a lower concentration than the usual one. In that case, if the lower concentration is used, then the equilibrium shifts left side, and that is why if silver ions are increased, the electrons will also increase. So in that case, if the electrode potential value is positive, it will become less positive, or if it's negative, it will become less negative. So it's asked, suggest how the electrode potential E for the silver ion silver electrode would change. So we'll write that the E value will become more positive, sorry, it becomes less positive or more negative as the equilibrium shifts, left hand side. That's how we are going to explain, because it just carries 1 mark. Okay, let's go ahead with the next part. It says define enthalpy change of the solution delta H solution. Now we should define that as an enthalpy change, or the heat change, enthalpy change when 1 mole of a solute dissolves, 1 mole of a solute dissolves in sufficient water to make a dilute solution, So that's the enthalpy change when 1 mole of a solute dissolves in sufficient water to make a dilute solution, and that's the enthalpy change of solution. Okay, here are some relevant data given for the changes of silver nitrate as shown in the table 4.1. Here is the enthalpy change of the solution silver nitrate, that is plus positive 22.6 enthalpy change of hydration of silver ions, that is delta H hydration of silver ions. Enthalpy change of hydration of nitrate ions is given. Complete the energy cycle of figure 4.1 to show the relationship between the lattice energy of AgNO3 and the energy changes shown in the table 4.1. Now lattice energy. Now what is lattice energy? According to lattice energy definition, then 1 mole of an ionic compound is formed from its ions in the ionic form, that is gaseous form, NO3 minus gas. That is how the delta H lattice is defined. So include the state symbols for all the species given here. Now here are all the stages given. AgNO3 in the solid form is given. Let's understand how to relate the enthalpy change of solution and hydration and lattice energy. Now we can see that there are already 2 arrows given here which is going down. Now if these are going down from the top, that is the reaction should be exothermic for this part as the arrows are going down, and that's possible. And here it's the silver nitrate given in the solid form. So that is possible only when we write silver ion in the gaseous form on the top and the nitrate ions in the gaseous form on the top, to show that this is the lattice energy. So this is how we should label it, lattice energy in the gaseous form. Okay, so from here we also need to relate the solution. So solution has to be an arrow going up showing that the silver ions in aqueous form and nitrate ions in aqueous form, that's called the enthalpy change of solution of the whole compound. But then we also have to relate the hydration of the ions. So first we can say that we can write hydration of, say, silver ions, that can be written silver ions. So then the silver ions changes to aqueous form, but then the nitrate ions remains in the gaseous form initially, because both these hydration cannot go together. And in the second step you can write hydration of the nitrate ions. That's the second step, where the nitrate ions from the gaseous form changes to the aqueous form. So this is how you're going to label the whole cycle, and you're going to write all the state symbols wherever required. So the top one, both are gaseous form. Here the silver ions are in aqueous form, but the nitrate ions are in gas form. Here both the ions are in the aqueous form. Let's see what's the next part. Next part is calculate the lattice energy of AgNO3. So in that case, if we want to find out enthalpy change of lattice, we have to write is enthalpy change of hydration minus enthalpy change of solution. That's how we can write, rearrange the equation and write it this way. And so hydration values, we can see that it is 475 and 314. So 475 plus, that is minus 300 and 314. Yes, 314 minus of plus 22.6, I think so. Yes, it's 22.6. Yes, if we use all these values, we get 811.6 kilojoules per mole. So 811.6, negative 811.6 kilojoules per mole. Let's go ahead. It says, suggest the trend in the magnitude of the lattice energy of metal nitrate, sodium nitrate, magnesium nitrate, and rubidium nitrate. Explain your answer. It says that suggest the trend in the magnitude of the lattice energy. Now, magnitude of the lattice energy, if we are talking about the metal nitrate, sodium, magnesium, rubidium, we should know its ionic size. So if we understand the ionic size, we know that sodium and magnesium are in the same period, and as the ionic size or the atomic size decreases along the period, magnesium is smaller and sodium is bigger. Now rubidium is in group 1 below the sodium. Okay, sodium, potassium, rubidium. So rubidium is even bigger. So you can say that magnesium is the smallest, then comes sodium, and rubidium is having the highest atomic size or the ionic size. And that's the reason the most exothermic is the one which is having the smallest ionic size. So we can say that magnesium nitrate is most exothermic, then the sodium nitrate, and then the rubidium nitrate. That's how we'll write. The reason being is that, as we have already discussed, that the ionic size matters. So as magnesium is having smallest ionic size, compared to sodium and rubidium. So magnesium, that is Mg2 plus, has the has the highest charge density. That's how I'll write highest charge density, because magnesium has the high charge and small size, so charge density of magnesium is highest. And as the same reason specifies that, so there is a strong force of attraction, strong force of attraction between the ions, strong force of attraction between the ions, and hence lattice energy is more exothermic, that is more value of energy is released out. So that's where we end up question 4 here, and it's question 5. And so now let's start with question 5 now. Question 5a says, in an aqueous solution, persulfate ions, that is H2OA2 minus, reacts with the iodide ions as shown in reaction 1. And the reaction 1 is given here. The rate of reaction 1 is investigated, and the sample of persulfate ions is mixed with a large excess of iodide ions of a known concentration. And the graph in figure 5.1 shows the results obtained. And here is the graph. Fine. So on the y-axis we can see there is a concentration of persulfate ions given. Yes, persulfate ions given, and on x-axis we have time in minutes. Now let's go ahead and read the next part where it says, use figure 5.1 to determine the initial rate of reaction 1 and show your working. Now if we are talking about initial rate, first thing, how do we calculate rate from the graph? That's from the gradient, and to find out the gradient we need to draw a tangent. Now if we were going to draw a tangent, then if they're talking about initial rate, we need to draw a tangent at time is equal to 0, that is on the first point. So let's draw a tangent here at the initial rate, that is at the initial time, that is 0 time, at the concentration 0.8. so let's draw it. Yeah, so here I've drawn a tangent for you, and if you want to find out the gradient, we need to subtract y2 minus 1. So gradient I'll say is y2 minus y1 upon x2 minus x1. If I take this triangle, that is this triangle which I've drawn, it's like 0.8 minus 0.150 here, and we can see this is on x-axis, it's 0 to 25. So x2 is 25, x1 is 0, and y2 is 0.80, and y1 is 0.150. so let's find out the gradient. Substitute it here as rate is equal to 0.800 minus 0.150 divided by 25 minus 0. That's how we find the gradient, and our answer is 0.026. so that's the rate we have found out. So rate is 0.026 moles per dm³ per minute. That's how we have found out the rate. Now in the second part says the rate equation for reaction 1 is rate is equal to rate constant K into the concentration of persulfate ions into the concentration of iodide ions. Suggest why a large excess of iodide ions allows the rate constant to be determined from the half-life in this investigation. Now if we want to find out the half-life in this investigation, we need to find out the rate of from the same graph at different time. If we want to do that, the concentration of persulfate ion is changed with respect to time, and if the concentration of persulfate ions is changed, the concentration of iodide ions should remain constant, and to make it constant we take it in a very large excess. So the reason is that to keep the concentration of iodide ions almost constant throughout the reaction, almost constant throughout the reaction, means we can change the concentration of persulfate ions but not the concentration of iodide ions. So to keep the concentration of iodide ions almost constant throughout the reaction. That's the main reason. Let's go ahead with the next part. It says the reaction of persulfate ions with iodide ions are catalyzed by Fe2 plus ions. Write two equations to show how Fe2 plus catalyzes the reaction 1. Now let's understand what is happening in reaction 1. Reaction 1, we can see that the persulfate ions are reacting with 2 moles of iodide ions to form 2 moles of sulfate ions and iodine molecule. Now this reaction needs a catalyst. The reason being is that both the ions are negatively charged and so it will repel each other, and that's the reason that the activation energy is very, very high. So in that case, we can understand that iodide ions to iodine is losing of electrons and persulfate ions to sulfate ions is gaining of electrons, and that's the reason that first the persulfate ions SO2 minus is going to react with Fe2 plus, which will gain electrons to form SO4 2 minus and Fe3 plus. Now if this is going to form, it's going to gain 2 electrons, so we need to use 2 Fe2 plus. Each will lose 1 electron to form 2 Fe3 plus ions, that is ferric ions. In the next step, the ferric ions, that is Fe3 plus, is going to react with the iodide ions, 2 iodide ions to form iodine, and again 2 moles of Fe2 plus are reformed in this second equation. So this is how the Fe2 plus catalyzes the reaction, decreasing the activation energy because of the similar charge, and this how the reaction is catalyzed. Okay, let's go ahead with the next part where it says describe the effect of an increase in temperature on the rate constant and rate of reaction 1. Now we already know that increase in the temperature always increases the rate, and if the rate is increased, the rate constant will also increase. So we can directly write that the rate of reaction 1, and rate constant increases with increase in temperature. So this is how we can explain also. Let's go ahead with the next part. It says in aqueous solutions, thiosulfate ions S2O3 2 minus reacts with the hydrogen ions as shown in reaction 2. Okay, here the thiosulfate ions are reacting with the hydrogen ions to form SO2 gas, sulfur and water. The rate of reaction is first order with respect to the thiosulfate ions and 0 order with respect to the hydrogen ions under certain conditions. The rate constant is given K, that is 1.58 into 10 power minus 2 per second. Calculate the half-life for the reaction 2. Now if the reaction is first order with respect to thiosulfate ions, we can use this formula of K is equal to 0.693 divided by T half. That's the formula we can use if the reaction is first order. So now it's given its first order with respect to thiosulfate ions, so we can directly substitute, and the half-life is given, that is rate constant is given, that is 1.58 into 10 power minus 2, which will give us the half-life. Fine. Because we want to find out the half-life, okay, again my mistake, we need to divide the rate constant, that is 1.58 into 10 power minus 2, and we get the T half. So let's find out T half, and it is 43.9 seconds. That's what my calculator is giving me the answer. Okay, next E part. E part says the compound nitrosyl bromide, that is NOBr, can be formed as shown in reaction 3. The reaction 3 is given here, where the nitrogen monoxide is reacting with bromine to form a nitrosyl bromide. The rate is first order with respect to NO, first order with respect to the bromine. The reaction mechanism has 2 steps. Suggest equations for the two-step of this mechanism state, which is rate determining step. Now we know that it is first order with respect to NO and bromine, and the bromine used here is one molecule, that is NOBr. You can make any of your mechanism, but we need to keep in mind that NO and Br, that is bromine, are first order with respect to our reaction. So what I generally do is that I always suggest my students that we can write it directly and make one molecule of the product directly. Now we know that there are two molecules of the product form and 2 moles of NO used. So we don't want to use 2 NO now. Yes, so I'm using one molecule of NO, that is nitrogen monoxide, with bromine to form one molecule of the product. Now we can say that one atom of bromine is left as a byproduct. So let's form that. And in the next step, again nitrogen monoxide, that is the second molecule. Here we can see there are 2 molecules of NO used. So in the second step, we are using the second molecule of NO and the byproduct Br, which is formed here to form the second molecule of the product, that is NOBr. So 2 molecules of the product form 2 moles of NO used and 1 molecule of bromine, that is Br2 used. And that's how you can definitely use your own steps, but according to your step you should remember that it is first order. Now for me the step 1 is for first order. Step 1, the reason being is that if both of it is first order, then till that step, which is rate determining step, both the reactants has to be used just once. If we use it twice, that shows that the reactant which is used twice is second order. So first order with respect to both the reactants, so I've used both the reactants once by step 1, and so step 1 is a rate determining step, and this is how I can explain also. Okay, here our next question gets over, that is question 5. Let's go ahead with question 6, where it says, question 6, A part, state what is meant by partition coefficient KPC. Now partition coefficient is the ratio of the concentration of a solute in two different immiscible solvents, that is partition coefficient. So you can, I'm repeating, is the ratio of the concentration of a single solute. The solute is not changing, it's the same solute, but the concentration is in 2 different immiscible solvents, so the concentration will be differing, and that ratio is the partition coefficient. Okay, the second part is the partition coefficient KPC of a compound X between the carbon disulfide and water is 10.5. So the value of KPC is given, that is 10.5. Now 1.85 gram of X is dissolved in water and made up to 100 centimeter cube in a volumetric flask. So now what are we doing? We are dissolving a solute X in water first and making it to 100 centimeter cube in a volumetric flask. 40 centimeter cube of these aqueous solution is shaken with 25 centimeter cube of carbon disulfide. The mixture is left to reach equilibrium, and calculate the mass of X in grams extracted into CS2, that is carbon disulfide layer. So what? So we first need to write the equation KPC is equal to the concentration of X into our organic solvent CS2 divided by the ratio of concentration of X in aqueous solution, that is water. Now the value is given, that is 10.5, and we don't know what is the you can say the mass of X which is extracted in CS2, but yes, that can be kept as X. Now that has to be divided by the volume of the carbon disulfide, that is 25 centimeter cube. Now understand, I'm not changing centimeter cube into dm cube because the same volume again I'm using in the denominator also. So here even if I add 10 power minus 3 and 10 power minus 3 here, that gets cancelled off, so it's not required. Even if you do it, that doesn't make any difference, you can go ahead and do it. Okay, so what about the mass of X in water? Now if earlier it was taken 1.85 gram in 100 centimeter cube, and out of that it was only taken 40. So what we need to find out is that if in 100 centimeter cube the X was 1.85 gram, then in 40 centimeter cube how much? So we need to find out in 40 centimeter cube by dividing it, cross multiplying it, and we get the answer is 0.74. So here that shows that in 40 centimeter cube aqueous layer, when we took the X, it was 0.74 present, and after shaking it with carbon sulfide, some of the X from 0.74 will go into the carbon disulfide layer. So if in X, that is in carbon disulfide, X gram of X solute is present, then in water leftover will be 0.75 minus X. That's how we can write, because earlier in water it was 0.74. Now out of that some X mass of the solute has gone into carbon disulfide layer. So what is left in the water is 0.74 minus X grams, and that's what. So if you simplify this reaction and find out the value of X, we get the answer as 0.642 gram. You just have to simplify this equation, mathematical equation, and find out the value of X given here. So that's how we find out the value. Let's go ahead with the next part. It says the compound C6H6 has many structural isomers. 4 suggested structures of C6H6 are shown in figure 6.1, that is Kekel's benzene, Dewar's benzene, and here is one more benzene and delocalized benzene. Fine. Okay. Now the question is, using figure 6.1, complete table 6.1 to predict the number of carbon atoms that have sp, sp2 and sp3 hybridization, Kekel benzene, Dewar benzene and the Lindenberg benzene. C6H6 structures are this: sp hybridized, sp2 hybridized and sp3 hybridized. Now what I simply suggest my students is that sp hybridization is present where there is carbon-carbon triple bond. Now in all the 3 structures we can see there is no triple bond. So in that case the sp hybridized carbon is 0 in any of the 3 structures. Okay, now if we look at sp2 hybridized, then number of carbon having C double bond C, that will give sp2 hybridized. So if we count here, carbon 1, 2, 3, 4, 5 and 6, all the 6 carbon have a double bond. So in Kekel's benzene there are 6 carbon having sp2 hybridization and there is no carbon left with CC single bond. All of the carbon have at least one double bond, so 0 for the Kekel benzene. sp3 hybridization is for the carbon-carbon single bonds. Now in this we can see that there are 1, 2, 3 and 4 carbon which is having a double bond. So I'll write 4 carbon with sp2 hybridization, and there is 2 more carbon with single bonds. So sp3 hybridization is 2 carbons. Now in Lindenberg's we can see that 1, 2, 3, 4, 5, 6, all the 6 carbon have single bonds, no double bonds, no triple bonds. So both sp and sp2 hybridization in the Lindenberg's benzene is a 0 and all of them have sp3 hybridization. So I directly write it as 6 carbon in the sp3 hybridization. Going ahead with the next part, it says describe the shape of delocalized benzene. Include the geometry of each carbon, that is CCH, bond angle, the type of the bonds between the carbon atoms, between the carbon and the hydrogen atoms. So geometry of CCH bond. Okay, let's understand the benzene structure for that. So if we understand the benzene ring, that is Kekul's benzene ring, we can understand that each of the carbon is having a double bond. So each of the carbon is having a double bond in its hexagonal ring. So we can write that in benzene, the carbon atoms are arranged in a hexagonal ring, Now if they are talking about geometry of CCH bond, that is CCH bond, this is H, this is C, this is C. Now if we know that there is an alternate double bond, then the carbon, if you talk about this geometry, is going to be a trigonal planar structure, because there is no fourth bond, there are only 3 bonds, and there is no lone pair on carbon left. Understand, if there is no carbon lone pair, on a center atom with 3 bonds in equal sides, is going to make a trigonal planar structure. So the geometry, so we are writing here in benzene, the carbon atoms are arranged in an hexagonal ring with CCCH geometry as is a trigonal planar structure, and in the planar structure the center atom has a 120 degrees angle with 120 degrees. That's what we write. So with CCH is a trigonal planar structure with 120 degrees. Okay, what's the next type? It says the type of the bonds between the carbon atoms and between the carbon and hydrogen atoms. So if we talk about type of bonds, we can describe that as a sigma bond or a pi bond. Now pi bond is present only when there are double bonds. So we know that between the carbon atoms there are alternate double bonds. So there are single bonds also and there are double bonds also. So we can write that bonds between the carbon atoms are sigma and pi bonds, and the bonds between carbon hydrogen are all sigma bonds, because they are all single bonds. There is never a double bond between. Obviously hydrogen doesn't form a double bond, so they are all sigma bonds. But between carbon there is single bond, double bond, so there are sigma and pi bonds both present. So that's how we'll describe the structure of a benzene. It's actually more than 2 marks, so we will definitely get full 2 marks. Next, suggest why Dewar benzene and the Ladenburg benzene are unstable isomers of C6H6. Now if we know the structure of the Kekulé benzene, we need to know that it's a planar structure where all the bonds, whether it's a C double bond C or C single bond C, they are all symmetric bonds with symmetric bond size also. But if you look at the structure of the Dewar and Ladenburg, we can see that there are certain double bonds, certain single bonds. So the bonds which are double bond will actually be smaller. The bonds which are single bonds will actually be longer, and that will how make this structure little strained structure, because the bond lengths are not same. So we can explain that. Suggest why they are unstable isomers. So they are unstable because the bond lengths between each carbon, or you can write all carbon atoms, each carbon atoms are not same, are not equal, you can write are not equal, and so the structure is strained, and so the structure is strained. Okay, next part. Complete table 6.2 to predict the number of peaks in proton NMR spectrum for the Dewar benzene, Ladenburg benzene and the delocalized benzene. So now understand we are talking about the proton NMR, that is hydrogen NMR in the three structures. With three structures, okay, Dewar, Ladenburg and delocalized benzene. These three structures, okay, 1, 2 and 3 structures. Okay, if we have a look at the Dewar benzene, we can understand that there are one hydrogen on each of the carbon, but here the two hydrogen are bonded to the carbon carrying the double bond, and same goes here. So all these proton bonded here going to show one type of peak because they are all bonded to the carbon carrying the double bond. But then these second protons here are bonded to the carbon which are having all the three single bonds. So this is going to show a second type of peak. So in the Dewar benzene we can write there are two types of protons. So there will be number of peaks of each proton will be 2. Now if we have a look at the Ladenburg benzene, each of the carbon will have one hydrogen and they are all single bonds. There is no strain and no double bond, nothing. Yes, so all these hydrogen atoms are going to show a single type of peak. So number of peak in this Ladenburg structure will be 1, and similar in delocalized benzene also, each carbon atom is bonded to one hydrogen and each of the carbon is having one double bond, delocalized benzene. So again the number of peak of hydrogen atom will be 1 because there is only one type of hydrogen. Fine, let's go ahead. Next part is F. The reaction of phenylethanol with 1,4-dibromobutane, that's given here, in the presence of ferric bromide, that is FeBr3, is shown in figure 6.2 here, and the reaction is whole shown. You can see it here that phenylethanol given here is reacting with 1,2-dibromobutane given here in presence of the catalyst, and the product is shown here with the byproduct HBr. Fine, let's go ahead. What are the sub questions shown here? The mechanism of this reaction is similar to that of the alkylation of benzene. Okay, construct an equation for the formation of electrophile shown here with a positive charge. Right, this is an electrophile we have to form, and that electrophile we know that's formed with the help of the catalyst we are using it here. So the reagent, that is 1,2-dibromobutane we are writing. Let's write that written here with the catalyst, that is FeBr3. Now that is going to form the catalyst, that's electrophile, which is shown here in the questions. We are writing it the same with a positive charge, and the catalyst will change into FeBr4 minus, right? This is FeBr4 minus. Should I write it here again? Okay, FeBr4 minus. So this is how the reaction is going to be possible for the formation of the electrophile shown here. Okay, let's go ahead with the second part. Complete the mechanism, the figure 6.3 for the reaction of phenylethanol with the electrophile ions here shown here. Include all relevant curly arrows and the charges and draw the structure of the organic intermediate given here. Okay, so we know the product is here and we need to draw the intermediate showing all the curly arrows. Now if this is the electrophile, we need to draw an arrow from the benzene ring to the electrophile here. Okay, now what are we going to show is show the same phenylethanol. Okay, here, so double bond O, single bond here. Fine. Okay, I've reconstructed my benzene because there should not be any extra lines here, which by mistake I drawn here. Okay, so we have 4 carbon bonded to the benzene ring, so I'm drawing the 4 carbon, 1, 2, 3, 4, and bromine here, that's the byproduct. Okay, that's the chain we can see here in the reaction. Yeah, that's the chain. Fine. Now what we need to be careful is then draw half the ring with a positive charge in between. Draw half the ring around the carbon at which the electrophile has attacked. So this is how it's going to be. And we also need to show one hydrogen because the hydrogen has not been lost yet. So this is how it's going to be. And the bond from the hydrogen, there should be a curly arrow being shown towards the positive charge, and that is the intermediate. Okay, now the byproduct, the full product is formed. That shows the hydrogen from the above product is lost as H+. So that's the byproduct which we have to show here. Okay, this is how we are going to construct the mechanism. That's the simple mechanism which generally is shown for the benzene also. Any electrophilic reaction of the benzene, we can show it in the same way. Third part next, the reaction shown in figure 6.2 forms small amount of two byproducts Y and Z. Suggest the structures of Y and Z in the boxes in the figure 6.4. Now we need to understand few points here is that the Z has C12, H14 and O, and it's C20, H22 and O2. Now O2 is where we need to add one more oxygen, and we can see there are more carbon atoms also added. Okay, that shows that there is compared to the byproduct here, there are 8 more carbon atoms in Y. Okay, what about Z? Now there are C12, 12 carbon atoms with hydrogen 14 and O. Let's understand what it can be. Okay, if we have a look here, there are 6 carbon here. This is the 7th and 8th carbon, 9th, 10th, 11th and 12th. So there are C12 similar. So Z also have C12. That shows that there is the product, byproduct is similar with the same number of carbon atom. But here we can see that the bromine which was here in our product is not present here. Plus if we count the hydrogen also, we'll understand that there are similar number of hydrogen atom, but only one hydrogen will be less. So what is the possibility? The possibility is that the bromine on this part, the carbon here, also acts as an electrophile, and that bonds to the other part of the benzene ring. That's how it's possible, because what is possible here is that there are 2 bromo present on the butane. One of the bromine is removed, and that the electrophile gets, or you can say the group gets added to the benzene. Same thing can happen with the second bromine also. So let's draw and understand what are the possibilities. So number of carbon atoms are not changing, so we also can't change. The similar diagram has to be drawn. A benzene ring. Okay, now what are the possibilities? 4 carbon atoms, so we can add 4 carbon atom ring on this side or on this side. Anything you can add. So I'm drawing it on the other side, so let me finish it. So I'm adding a 4 carbon side chain here. So these are the 4 carbons I've added. 1, 2, 3 and 4. 4 carbon ring I've added here to the benzene. So it's going to be C12, H14 and O. Let's understand how H14. There are 3 hydrogen atom on this chain. No hydrogen on the second carbon chain. Then there are 4th, 5th, 6th, 7th, 8th, 9th, 10th. Okay, now understand this carbon have 2 hydrogen on each carbon, right? So if you count it that way, then 6, 7, 8, 9, 10, 11, 12 and 13, 14. There are 14 hydrogen done. Yes, so this is the byproduct possible with only, okay, by mistake I've drawn it in Y. This diagram has to be on the Z part. Okay, I'm redrawing it here. Okay, again I made a mistake. Always understand the benzene ring has to be drawn properly. I cannot draw over lines on the benzene. Okay, I'm drawing the 4 carbon ring, and this is how it has to be drawn. I have to rub out from the Y here. Okay, now about Y, as we know that there is one more bromine and the same carbon carrying the bromine will undergo the similar reaction. Now we can understand that there is C20. So C20 means there are 8 more carbon atoms added. Now you know that the benzene ring here, that is phenylethanone, have 8 carbons. The 6th carbon here, the 7th and 8th here. So if the same ring is added on the other part of these bromobutane, then the similar reaction will happen. So let's understand and draw the same part. Okay, so I'm drawing it first here, the same benzene ring. Okay, here are the same benzene ring. Then we have the 4 carbon chain here. So 1, 2, 3, 4. Now on the 4th carbon again the same benzene ring will get bonded. So same thing can happen. Okay, so let's draw it again, the same benzene ring getting bonded here. Now if you count the carbon atoms, the hydrogen atoms and the remaining part, all the oxygen, you will see that it matches C20, H22 and O2. So this is how the byproducts can be formed. That is because of the presence of the second bromine on the incoming group. So understand that way, that if one of the bromine is undergoing a reaction, the same reaction can be can happen on the second bromine also. So that's how we have understood and drawn the byproduct here. Okay, so this is the end of this question, and we'll discuss the remaining 3 questions in the next video. So in this video we have discussed question 4, 5 and 6. In next video we'll be discussing questions 7, 8 and 9, and I hope all the questions and answers are very clear.